Hi, I'm Ryan Blodgett.
I'm Rivera. For our senior design course, we developed a hands-on multi-axis CNC project that will be incorporated into an advanced machining class for the Industrial and Manufacturing Engineering department here at Cal Poly.
Our technical advisor for this project was Treon Giorgio.
Here is the agenda for this video. We will start by restating our problem statement, followed by introduction of our goals for the project. Then the part fixture, part blank, and soft jaw design and toolpaths. We will briefly go over the documentation, including drawings, routing, and operation sheets. This will be followed by machine and tool setup. And finally, you will get to enjoy our machining video.
Our problem statement is that few universities offer a hands-on course in multi-axis CNC machining due to a lack of published curriculum on the methodology and hands-on approach to teaching multi-axis machining. Currently, there is an absence of a turnkey multi-axis CNC lab project for educators to utilize in their machining curriculum.
Our project describes the methods of creating a comprehensive multi-axis computer numerical control or CNC machining project for the Industrial and Manufacturing department here at Cal Poly. Students will learn the fundamentals of multi-axis CNC machining, which incorporates 2 rotational axes in addition to the traditional 3 linear axes. This greatly increases capability and accuracy of the CNC machining process. Students will also learn the design process, which includes the designing of their part using CAD, computer-aided design software, and creating toolpaths and parameters on computer-aided manufacturing or CAM software. Finally, students will gain experience setting up and operating the multi-axis mill in accordance with engineering drawings, routing sheets, and job setup sheets. The goal for our part design was to incorporate various features to showcase the increased capability of multi-axis machining. Other important design considerations were attention to machinability and repeatability due to the fact that this will go on to be used for educational purposes. Using SolidWorks, we created a part with 3 45-degree faces, each with a different feature on them. In between each of these features is a small round extrusion with a drilled and tapped hole. There are several DFM or design for manufacturing principles to keep in mind when designing a part. For example, a 3-to-1 length to diameter rule must be considered when machining a flat pocket, such as the one here, in that the length of the tool in contact with the material must not be greater than 3 times the diameter of the tool.
With the demo part completed, the next step is to create the mill fixture. This part is going to hold the workpiece in the collet of the Haas T5C. The 3 main functional requirements of fixture design include locating, holding, and supporting the workpiece during machining operations. In doing so, provides a way to repeatedly align and reference a cutting tool to the workpiece. Locating the demo part on the fixture requires eliminating the 6 degrees of freedom of which a part can move in space. So this flat surface right here is going to mate up with the bottom of the workpiece, and that's going to restrict rotation about the X and Y axes and on the Z axis. This boss right there is going to restrict movement along the X and Y axes. The locating pin will eliminate another rotational degree of freedom, and then the set screw on top right there is going to eliminate the final degree of freedom by threading into the fixture itself. Here you can see the outer diameter is going to be turned down to be smaller than the diameter of the part, and that is to avoid any collision of the tooling.
Alright, now with our fixture designed, the next step is to create a blank that will be held in the mill fixture and serve as the stock that the demo part will be machined out of. Here is our blank. You can see there are features on both sides, so it will require 2 separate operations. A section view reveals some of the internal features. We've included a hole for the locating pin, a pocket that the boss on top of the fixture will mate to, and a hole for the set screw to secure the part to the fixture. Now, in order to machine the features of the mill blank, a set of soft jaws were created to hold the part during the two brief machining operations. As you can see here, we chose a pocket with a depth of 0.6 inches in order to securely hold the part. And I'll show the blank inside of the soft jaws like so. And again, there will be one operation on this side and then a second operation on the other side, in which the part can simply be flipped over. Once the designs for the part and fixture are created, we need to create tool paths using CAM software. In our case, we're using HSMWorks. So this is done by choosing a specific type of tool path and selecting the geometry on the part where the cut will be made. Certain considerations for CAM include tool selection, feeds and speeds, depth of cut, step over distance, and plunge rate, in addition to the selection of a home location. We're going to show you the CAM for the actual part. The yellow represents the stock that's going to be cut away, or in other words, the mill blank. So it's going to start by facing those 345-degree angles. That's going to create the flat surface where our features are going to be put in. Next, we're going to come in with an end mill and machine these vertical pockets. After that, we're going to drill and tap the holes, each of those holes. Next, we're going to come in with another end mill and pocket this flat section here, followed by, slowing down here, an adaptive cut of the circular pocket here. And we're going to have a finishing cut with a spiral tool path, followed by a contour cut, which will take away the stock that is left around the circumference of the part. We need to add chamfers for the pocket and the holes, and then finally we're going to finish up the part with an engraving step shown here. With proper engineering and manufacturing procedures, all of the proper documentation was created for each part that was machined. This includes drawings. All of our parts have drawings. Here's the fixture along with our demo part, and of course the blank. Drawings are important because they communicate specific requirements and tolerances consistently between the engineers and the operators who fabricate the part. In addition to drawings for each part, we also have routing sheets for each part. Routing sheets list every manufacturing and processing operation in the order which they are to be performed. They also include the operation number, a description, the machine tool, and the required tooling in addition to the operation time.
Here we have an operation sheet, and these are created for each machining operation, specifying everything needed to set up and run the operation. And that includes the material, the tooling, even the program name, what home location we're using, either G54 or various other options, and all of the tooling numbers involved. And here you can see the operation number, which is 140, which is the final operation. And here are all the tool numbers. Here is the tooling description, surface speed, RPM, chip load, and all vital information for machining the part. Here's a rundown of each tool and what operation they're used for. First, we have our 2-inch 5-tooth face end mill. Next, we're going to move on to our 1/4-inch ball end mill, and that is for the 3D pocket. Tool number 3 is our 4-flute 1/4-inch flat end mill, and that is for the 2D pocket. Moving on, tool number 4 is our chamfer tool. Next, we have the drill, And then tool number 6 is our 16th inch ball end mill for the engraving operation. Last three we have our 1/4 tap, the 3/4 inch flat end mill for the contour on the outside, and last but not least we have our 3/8 inch flat end mill, and that is for the vertical pockets. Here we are setting up the Haas tool lathe 1 for some turning operations. First, we're going to touch off the tool in the X axis, and we're going to make sure the part is stopped. And we're going to hit the X offset, and then we're going to enter in the workpiece's diameter to give the correct offset. Now the next step is to come in and touch off in the Z axis as seen there, and then we're going to hit the Z axis offset, and you can see the tool offset right there, and that is it. Here we are setting up the Haas VF2 for some mill blank operations. The first step is to insert the tool into the spindle and then touch off the tool. This is done using the Renshaw optical tool setter, which is a 3D touch tool trigger that uses quick code to create the tool offsets. And all we have to do here is just put in the tool number, and then the machine will do the rest. It is creating the quick code right now. We just hit cycle start, and then the tool will touch off, as you can see, and then it will generate all the offsets needed. Analysis. For every quarter, we're going to assume 50 students. Now, moving into the 3-inch bar stock of aluminum, we're going to assume that each student will be given 2 inches, and that will make it out to $480. Next, for the stainless steel, we're going to assume 12 inches for the fixture just in case we have a defect. So that's going to make it out to $107. Add those two together, that's going to give us $587. And then tooling for the quarter, we're going to assume that they only last for 1 quarter. And we have 16 different cutting tools, and that's going to come out to $517.61. So the grand total is $1,104.61, and that is our cost analysis.